Hi all, today I'm going to be talking about using indirect truth tables to figure out if arguments are valid or invalid. Up until this point, we've used truth tables to figure out if arguments are valid or invalid, but that, as you may have noticed, can lead to a lot of work. So take this argument for example. If we were going to use a truth table to figure out if this argument in the middle of the page were valid or invalid, we'd first have to calculate how many lines our truth table would have. So that's 2 to the nth power, where n is the number of unique variables. So in this argument, we have a j, an l, a k, an m, and an n. So we have 5 unique variables. So the number of lines would be 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th power. So we'd have 32 lines in our truth table. And we need to figure out the truth value for all of these propositions, or at least a handful of them on each line. And that can take a lot of time. So today, by the end of today's lesson, we're going to learn how to figure out in one line if this argument is valid or invalid. And to do that, we'll be using indirect truth tables. Over to the right-hand side of the screen, I have the steps that you take to use an indirect truth table to figure out if arguments are valid or not. Over here to the left, I have my truth tables for the various operators that we use. But before we get to all that, there's a skill we need to pick up, and that skill is working backwards to determine the truth values of statement variables. Up until this point, we've been given the truth value of statement variables, and we've had to work up to the truth value of complex statements or complex propositions. What we're going to be trying to do now is learn how to go backwards from the truth value of the complex statement or the complex proposition to the truth value of the individual statement variables. So let's see how that works. First, take an easy example. If you know tilde A is true, so we see that because there's a capital T underneath the tilde there, or the hyphen in our case. So if tilde A is true, then A, because, look, if tilde A is true, let's go here, if tilde A is true, then the A must be false, because if tilde P is true, then the P must have been false. So A, in this case, would be false. So far, so good. Let's get into progressively more complex versions of these problems. And if you get it at any point, you can pause it and try to do the problems yourself and come back and see if you got the same answers that I did. So here in this problem, we're given A or B is, let's do it this way. We're given A or B is false. And we're given that A is false. What would we know about B? Well, the only time a wedge is false, if we look over at our truth table over here, is when both parts are false. So A would be false, but also B would have to be false for that wedge to be untrue, for that wedge to be false. All right, how about, let's delete these. How about A horseshoe B? What if we know that A horseshoe B is false? What do we know about the truth value of A, and what do we know about the truth value of B? Well, if I look at my truth table for a conditional statement, then I see that a conditional statement is only false on one line, when the part before the horseshoe, the P in this case, is true, and the part after the horseshoe, the Q in this case, is false. That's the only time when a horseshoe is false, when the antecedent is true and the consequent is false. So if I know that a horseshoe is false, then I know the antecedent must be true and the consequent must be false. So just knowing that the horseshoe is false tells us what the truth value is on both sides of the horseshoe. Carrying on, if I have A if and only if B, and if I know that that triple bar is false, and I know that B is false, can I solve for the truth value of A? Well, if I look at the truth value for the triple bar, I see that the triple bar is only false when the things on both sides of it are unequal. So if this triple bar is false, the things on both sides are going to have to be unequal. So because one side is false, in order for this to be false, the other side's going to have to be true. So the A has to be true, and the B, if the B is false and the triple bar is false, then the A has to be true. All right, how about A dot B? What if I know that that statement is false? So A and B. If I look at my truth table for conjunction, I see that there are many ways that a conjunction can be false. There's only one way that it can be true, if both sides of it are true. But there are many ways that it can be false. The first part can be true and the second part false, the first part false, the second part true, or they can both be false. So if I'm given that this is false, I can't solve for A and B. I don't know what the truth value of A is, and I don't know what the truth value of B is, just given if it was false. If I was given that it were true, I would know that A would be true and the B would be true. But I don't know A because A could be true or false, and B could be false or true. There could be 3 different combinations of truth and falsity for the combination of A and B, and it being false. So how about if A then B? If I'm given that if A and B is true, and if I know that A is false, can I solve for the truth value of B? To solve that, I'd look at the truth table for a conditional statement, and I would see that when the antecedent is false, the statement is true regardless of whether the consequent is true or false. So here I cannot solve for the value of B. I'm not given enough information to do it yet. All right, how about if A then not B, and if I'm told that this is true? Let's take a look at the truth table for conditional statements. If we do, we see there are many ways that this can be true. It could be that A is false and then B could be either true or false. Or if A is true, then B has to be false because the tilde would flip it around. But either way, I cannot solve for this truth value. Let's change this problem a little bit. Let's say we know that A is true. Now can we solve for the truth value of this proposition? Well, if A is true and this horseshoe is true, then the consequent cannot be false, because if I'm looking at the truth table for conditional statements, the only time when it's false is when it's true, horseshoe, false. And I'm told that this is true. So it can't be that the consequent is false. So the other part will have to be true. So I'm going to put under the main operator of the consequent, true. And then if tilde B is true, then B itself would be false. So if I were given that this were true, and if I were given that A were true, then I would know that B would have to be false. Let's change this up a little bit again. What if I knew that B were true? Could I solve for the truth value of A? Well, if B is true, then tilde B would be false. And now I have a conditional statement that we're told is true and that has a false consequent. So if I have a false consequent, and I had a true antecedent, it'd be false, but that would be a contradiction. So if I have a false consequent and a true conditional statement, then I need a false antecedent. So A here would be false. All right, let's do one last problem like this, and then we'll move on. Let's say I had A, horseshoe, B, or C, and I was told that this was false. Could I solve for the truth values of A, B, and C? The answer to that is yes. So if I'm given a false conditional statement, then I know that the antecedent has to be true and the consequent has to be false. So what's the antecedent here? It's really simple. It's just A, so A would have to be true in this case. And I know that the consequent has to be false because the horseshoe is false, and it's only false when it's true false. So then if B or C is false, the only time that a disjunction is false is when both parts of it are false. So B would have to be false, and C would have to be false as well. So just by given that this horseshoe is false, I know that A is true, B is false, and C is false. I'm able to solve for the whole thing. So now let's put this skill of working backwards to determine the truth value of statement variables together with the step-by-step instructions over here, and then we have everything we need to do an indirect truth table to figure out if an argument is valid or not. So let's take a simple argument first. A horseshoe B, C horseshoe B, therefore A horseshoe C. So if A then B, if C then B, therefore if A then C. The first step we need to do is rewrite the argument horizontally with slashes between the premises and a double slash between the last premise and the conclusion. So same step we would take with a normal truth table. So we do that. First premise, slash, second premise, double slash, conclusion. Now what we're going to do is assume that the argument is invalid. Now, what does it mean that an argument is invalid? It means that true premises do not guarantee a true conclusion. So that means if we were doing a regular truth table, there'd be some line, some combination of truth values for the statement variables such that all the premises were true and the conclusion were false. Now, if we're assuming that the argument's invalid, we're going to assume that that line exists, and we're going to work backwards to the truth value of the statement variables. So assume that the argument is invalid. Assume that there's some combination of truth values such that all the premises are true and the conclusion is false. So then we're going to write true under the main operator of all the premises and false under the main operator of the conclusion. So let's go ahead and do that. So A horseshoe B, we're assuming there's a case where it's true and C horseshoe B is true and that A horseshoe C is false. We're assuming that all of this can happen in the same, with the same combination of truth values for A, B, and C. So now we need to solve for the truth value of all variables, attempting to avoid contradictions. So let's start with the conclusion first. If we know that A horseshoe C is false, what do we know about A and C? Well, the only time a conditional statement is false, again, is when the antecedent is true and the consequent is false. So if A horseshoe C is false, then A is true and C is false. Now that we've figured that out, wherever we see A in this problem, we're going to write true. Wherever we see C in this problem, we're going to write false. So we've figured out that A is true. We've figured out that C is false. So now we keep solving. And what we're trying to do is avoid contradiction. We're trying to avoid contradicting ourselves. So we'll keep solving. So C is false and this horseshoe is true, what does that tell me about B? That doesn't tell me anything. Note I'm working from back to front in this problem. That's sort of the way I like to work these problems, but you can find your own way. I just suggest that you do the conclusion first. That will be helpful because you can often glean a lot from the conclusion. So if this is true and C is false, well, it doesn't matter what B is, so I can't figure out the truth value of B from this premise. So let's go to the other premise and see what we can figure out. If this conditional statement is true and A is true, then B has to be true. Otherwise, I'd be in a situation where the antecedent was true and the consequent was false, but I would have said that the conditional statement were true, and that would be a contradiction. But I'm trying to avoid contradicting myself here. So, if A horseshoe B is true and A is true, then B has to be true. And then I'm going to fill in B here. I'm going to fill in true for B here. And I'm going to see if this worked out here, this C horseshoe B and this assignment of truth values, because it's the last thing I solved for. So I said C horseshoe B was true, C is false, and B is true. Have I contradicted myself? No, that totally works. False horseshoe true is true if we look on this line of the truth table. So what have I done? I solved for the truth. I assumed the argument was invalid. I wrote true under each of the premises, and I wrote false under the conclusion. And I looked to see, is there an assignment of truth values that would make the premises true and the conclusion false? And there is one. It's when A is true, B is true, and C is false. In that case, the premises are true and the conclusion is false. I assumed that the argument was invalid, and I was able to solve for everything, and I avoided contradicting myself. So, if I don't reach an inevitable contradiction, then my assumption that the argument is invalid was correct, and the argument is in fact invalid. So I didn't reach any contradiction. I solved for all the truth values of the variables. So this argument is invalid. So let's look at what happens when we do reach a contradiction and show you what that looks like. Because if we do reach a contradiction, an inevitable contradiction, then our assumption that the argument was invalid was correct, and the argument is actually valid. So if you reach a contradiction, the assumption must have led you down the road of that to that contradiction, so you have to revise your assumption. All right, so let's look at this argument. If not A, then B or C, not B, therefore if C, then A. We're going to follow these steps again. Well, we already rewrote the argument horizontally. Assume that the argument is invalid. So we're assuming that there's some combination of truth values such that the premises are true and the conclusion is false. So we're going to do true under the main operator of each premise, and false under the main operator of the conclusion. And now we're going to solve for the truth value of all variables, attempting to avoid contradiction. So if C horseshoe A is false, then we know that C has to be true and A has to be false. So now I'm going to fill in true for C wherever I see it in the problem, and fill in false for A wherever I see it in the problem. So here's a C, that's going to be true, and here's an A, that's going to be false. So now I keep solving. Let's start by going with B here. So here's, should we start here? True. Yeah, let's start right here. If tilde B is true, then B itself had to be false. and then we'll fill in false over here and see what we come up with. So now we're going to solve for the truth values under this, for this argument. So here we're saying this is true. So if A is false, then tilde A is true. We're told that this is true. So then over here we have F, we have false, wedge, true. And that will be true. So here actually we didn't come to a contradiction. Let me redo this problem real quick. So we didn't come to a contradiction, so this argument would be invalid. We were able to solve for the truth value of all parts. But I'm going to make one small change. I'm going to change that wedge to a dot. Alright, so now let's run the steps for this problem to see if we can generate a contradiction here. So underneath the main operator of the premises, we're going to write true. Underneath the main operator of the conclusion, we're going to write false. That's because we assumed it was invalid, so we're assuming there's some combination of truth values of the variables such that this can be the case, that the premises are true and the conclusion is false. And now we're going to solve for the truth value of the statement variables. If C horseshoe A is false, then C must be true and A must be false. So wherever we see A, we're going to write false. And wherever we see C, we're going to write true. And now we're going to keep solving. So if tilde B is true, then B itself is going to be false, and we're going to put false under the B here. And now we've solved all this over here, so let's see if everything we have here works out. So if A is false, then tilde A is true, and then we have true, horseshoe, true, we have true for the antecedent, and we're saying the conditional statement is true, so the consequent better turn out to be true. Well, we have false and true. False and true is false. And now look at what we have. We have a conditional statement that we said was true, and we have a true antecedent and a false consequent. Note, that should be setting off alarm bells in your head. True, horseshoe, false should be false. So what we were led to here was a contradiction that was inevitable given our assumption that the argument's invalid. Because we have true, horseshoe, false being true, and that should hurt your brain at this point in the course. So what happens when we've contradicted ourselves? If we reach an inevitable contradiction like we did, then our assumption that the argument was invalid was incorrect, and the argument is actually valid. So there's no assignment of truth values for this problem such that the premises are true and the conclusion is false. So this argument is valid. Finally, let's do this last problem. So this was the problem we said we could solve by the end of the lecture today. Let's see if we can do it. So rewrite the argument horizontally. We did that. Assume the argument is invalid. That lets us write T under the main operator of all the premises and F under the main operator of the conclusion. So let's go ahead and do that. main operator here is the horseshoe, the horseshoe, the horseshoe, and again, the horseshoe. So we're assuming there's some combination of truth values for the statement variables such that the premises are true and the conclusion is false. Let's see if we can find that. So if J horseshoe N is false, then J is true and N is false. So wherever we see N, we're going to write false. And wherever we see J, we're going to write true. All right, so if N is false and this horseshoe is true, then L or M is going to have to be true. That doesn't give us much because there are many ways that a disjunction can be true. 3 different ways, so we don't know the truth value of L or M from that. So let's head over to here. If we know that J is true and that this horseshoe is true, then we know that the consequent must be true. Sorry, let me come back over here. So if I know N is false, and if I know this horseshoe is true, then L or M has to be false. Because if it were true horseshoe false, then I would have a false horseshoe, and I can't have that. So if I know that L or M is false, that actually tells me a lot. That tells me that both parts of it have to be false, because there's only one way that a wedge is false, and that's when both parts are false. So L or M are false. That's what we just learned. So where we see L or M, we can write false. L is false there and false there. All right, so now we keep solving. So if L is false, then tilde L would be true. And if tilde L is true, then we have true horseshoe false, because M is false here. So inside the parentheses here, we would know that that statement is false. And if that statement is false and the horseshoe is true, then we know that the antecedent has to be false, because otherwise we'd have true horseshoe false being true, and we're trying to avoid contradiction. So now we've learned that K is false. So we'll fill in K over here as false. And now we'll see if this works out with this assignment of truth values, if this will be true. So we have J being true and the horseshoe is true, so we have to have a true consequent. So if L is false, then the tilde will flip that to true. And if K is false, then the tilde will flip that to true. So then we have true, horseshoe, true, sorry, let's do it this way. True, horseshoe, true, and that is true. And so then we have true, horseshoe, true as being true, and that works out. So what have we done? We found out, we've solved for the truth value of all the statement variables such that their premises are true and the conclusion is false. So this argument is invalid. What we did essentially was shortcut our way to the line, the assignment of truth values where the premises are true and the conclusion is false. And that line would be, so J, L, K, M, N. That would be the line where J is true, L is false, K is false, L is false, M is false, and N is false. So we shortcut our way to this line, where j is true and everything else is false. What line would that appear on? We said there would be 32, so we said there would be 32 lines to this truth table. On the first half, j is true. The one right before it starts being false is the one where j is true and all the rest are false. So we would have to have done 16 lines on this truth table to figure out that this argument is invalid. We shortcut our way down to line 16 by doing this indirect method, saving ourselves 15 lines of work, which is great. And sometimes if you add one more variable, that would be 64 line truth table. You don't want to do that. So what did we learn today? We learned how to do indirect truth tables to solve to figure out whether arguments are valid or invalid. That's especially useful when you have arguments that have very many statement variables. How did we do that? We learned how to work backwards to determine the truth values of statement variables when we're given the truth value of complex statements or propositions. We learned the steps we need to follow to do the indirect truth table, and we used them to figure out if arguments were valid or invalid. Hopefully that helped, and I'll see you next time.